lecture of the CAM 810S course. The subjects are drive systems, measuring and feedback systems, and end effectors. We start with power transmission systems. They should be light in weight, small in size, backlash-free, and maintenance-friendly. The timing belt, or toothed belt, or synchronous belt drive, as it is also called, is both backlash-free and light in weight. Our ER4U robot arm in the laboratory is equipped with timing belts. Planetary drives are compact in size and provide a good reduction ratio. Harmonic drives are compact sized, provide an excellent reduction ratio, are highly precise, and light in weight. After the lecture, you may watch YouTube videos which show how planetary drives and harmonic drives work. Robot arm drives need measuring systems which provide information about the exact position and the velocity of each axis. The measured variables are transmitted to the controller. The controller computes these variables constantly, compares them with the set value, and feeds eventual corrections back to the system. We call this type of control a closed loop control. It is clear that each axis of the robot arm must have its individual measuring system. This simplified graphic shows the closed loop control of a robot axis. The program defines the set value of a position to which the axis must move. The controller sends this set value to the motor, which drives the power transmission. The axis moves to the determined position, and the measuring system provides information regarding the actual position of the axis. This information is then fed back to the controller, which compares it with the set value and feeds eventual corrections back to the system. This complex process takes place in milliseconds and on all axes of the arm at the same time. Position measuring systems in rotary axes are called rotary encoders. Incremental rotary encoders are so constructed that a light-emitting diode, short LED or LED, emits a light beam. After passing through a lens and the blind, the light beam proceeds towards a slotted disc, which is called encoder disc. If it meets a slot, the beam passes through this slot and strikes a phototransistor, which sends a signal to an amplifier. If the light beam meets a space between two slots, it is stopped and the phototransistor does not send a signal to the amplifier. Since the disk rotates, the digital output is alternatingly sending on and off signals to the controller. This is a so-called signal period. The properties of incremental rotary encoders are the robot arms equipped with this type of encoder must be homed. That means that a reference point must be defined after switching the controller on. Incremental rotary encoders may lose signals and are therefore relatively failure-prone. Because of their simple design, they are relatively inexpensive, which is an advantage. Our education robot arms CoreBot ER4U uses incremental rotary encoders and must therefore be homed after switching the controller on. Unlike the incremental encoder, the absolute rotary encoder can detect unique positions. The general setup is similar to the previously discussed one, but the encoder disk has several concentric rows of slot, not only one. Each of them has its own light-emitting diode and its own phototransistor. The disk on the right side of this graphic has 5 concentric rows and can therefore provide a so-called 5-bit dual code of on and off signals. The 260 degrees of the disk's circumference are subdivided into 32 segments. The disk can therefore send 32 times 5, that is 160 signals in one complete revolution. Since the absolute rotary encoder can detect unique positions, no homing is required. A robot arm, which is equipped with absolute rotary encoders, is operational right after the controller is switched on. This is the case with practically all industrial robots. Operation is near failure-free. It is clear that an absolute rotary encoder is much more expensive than a simple incremental one. You may watch a YouTube video which shows how absolute rotary encoders work. Another way to detect the angular position of a rotary axis is the use of a so-called resolver. A resolver looks similar to a small electric motor. Its properties are that no calibration is required. It is of a simple and sturdy design, and it has got a near failure-free operation. But it is not always 100% reliable and not very accurate. Some robotic applications required an accurately defined velocity of the end effector, such as, for instance, welding, spray painting, cutting, drilling, and others. The velocity of the end effector may be determined by measuring and computing the angular velocity of the arm's encoder disks. Another possibility to measure velocity is the take-curve generator. Take-curve generators provide a voltage which is proportional to the RPM of an axis, as you can see in the diagram to the right. Its properties are it gives a linear output signal. It is not influenced by temperature changes, and it is maintenance friendly because it is brush free. They are also highly reliable, but on the other hand, also quite expensive. Now we are going on to end effectors. In robotics, an end effector is a device or tool that is connected to the end of a robot arm where the hand would be. We distinguish between grippers. A gripper picks objects and places objects. And tools, such as, for instance, spray guns, welding guns, drills, screwdrivers, and many others. In practically all handling applications, object parts have to be picked in one place and transported to another and released there. We speak about pick and place applications. The device which serves this purpose is the gripper. The model for the gripper is the human hand. But we usually do not need such a sophisticated and expensive hand. The simplified design is adapted to the shape and type of a part to be picked. There are three methods of gripping an object: by friction, by encompassing the object completely, and by adherence. According to their specific gripping tasks, grippers have different designs. This is a mechanical two-finger gripper. The fingers swivel out and in. Whereas this one is a mechanical two-finger parallel gripper. The difference is that these jaws of this gripper, move absolutely parallel. There are also pneumatic grippers, widely used, with exactly the same types of fingers. That means two-finger gripper and parallel gripper. Both of them, as we said, pneumatic. For cylindrical objects to be picked axially, three-finger pneumatic grippers are used. A quite interesting concept is the so-called encompassing gripper, which is used for delicate objects. In the next slide, you will see how it works. Then there are the magnetic grippers used, but of course limited to ferrous objects, and widely used vacuum grippers, which are also explained later. The encompassing gripper is made of a soft material, a kind of skin which encloses air. The gripper approaches the object in a soft state. Because it is soft, it deforms around the object. Then the air is evacuated and the skin closes around the object. And now the object can be manipulated or moved. There is also a video on encompassing grippers, which you may see later on. Vacuum grippers are used for smooth, clean surfaces, normally of quite large but not heavy objects. This example shows the grasping or gripping of a large sheet of furniture with several pneumatic cups. Springs enable the vacuum cups to be pressed firmly against the object so that all objects that would be OI8, so that all cups are being able to contact the material. This is the end of the fourth robotic lecture. Thank you for your attention.